Okay, so hello everyone. Welcome back to the very final lecture of our 2-month long school. So before we get into our topic for today, I'll try to recap a few things so that we're all on the same page. Okay, maybe it's best to start from the Glashow-Salam-Weinberg model. So where did we stop? We started where did we start? We started discussion with the following idea that let's propose a gauge group such as this, SU2 left times some U1 hypercharge. We saw what hypercharge is yesterday. And what we wanted to do is have the similar idea that we have been building up for via the means of spontaneous symmetry breaking. So with that, we first specified our gauge fields for the SU2 part. It's this guy. For the U1 hypercharge part, we had a gauge field like this. So what was our requirement for describing electroweak interactions or weak interactions in the first place? The idea was that we need to have massive spin 1 gauge fields and that weak interaction violate parity or handedness. So for example, only left-handed neutrinos feel the weak interaction. So we wanted these two requirements. With that, we did proceed with defining a scalar again, introducing a scalar h, which is a complex scalar. And we then went on to write out the Lagrangian, the potential for the scalar. And then we again did our usual thing that we have been doing, is we pick a minima, expand around the minima. And then we found that there are, of course, from our previous analysis and intuition, of course, even before doing the calculation, we could say that these were the Goldstone modes, and which appear in a certain combination, such as this. And then we plug that in by taking fluctuations around the minima or expanding around the minima. We plug that in the Lagrangian. And then what happened is that we saw, uh, of course, the familiar massive scalar is there. And then what we did is we moved to a more convenient basis. What happened was when we moved to this basis, we saw that we have three massive gauge bosons, which are the W plus minus. This is the Z boson and W plus minus, and they have their corresponding masses. And more interestingly, a massless gauge boson or a massless spin 1 gauge field, which was very interesting because this actually did correspond to the U1 gauge field of electromagnetism. So in the process of studying the weak interactions, we actually discovered that at high energies, that is above the scale of spontaneous symmetry breaking, electromagnetism and weak interaction are part of the same force, which is quite amazing. And then we saw that how this might correspond to the photon, and we did that because it corresponds to the U1E electromagnetism generator, which is Q, electric charge. And that's what we saw. And then we moved on and we put this analysis again, just a recap of this in the light of Goldstone's theorem, and we saw that, okay, there should be three Goldstone bosons. However, some part of it I would like to mention about the weak interactions is that so far we had we have described the following two phases of gauge theories. One, which we call the Coulomb phase, which is basically QED, for example, with with long range interactions mediated by. So in this phase, in the Coulomb phase, there's no spontaneous symmetry breaking, and all massless gauge fields. There's another phase, which we call the Higgs phase. And of course, as you guessed, for example, if you want to give an example of this, GSW is an example of a Higgs phase with SU2L, which of course gets broken to U1, E and M. And this has the spontaneous symmetry breaking mechanism actually generates three massive mediators plus, so these are short range interactions, of course, because these guys are massive. And of course, the Coulomb phase guy. Okay. So these are the two phases of gauge theories. And then we come to the case of the final discussion, which is the case of strong interactions. So first thing to ask is, can strong interactions be described by a QFT? Can the short range story of Glashow, Salam, Weinberg work here as well? Because of course we don't see the strong force in action. There has to be a reason for that. Maybe it's spontaneous symmetry breaking. Is that so? So the third question is that it's related to the point that I made. Are there other phases of gauge theories? Okay, that can describe the short range interactions. So the answer to 1 and 3 is a yes, which is very interesting. And number 2 is no. So you cannot have a spontaneous symmetry breaking kind of mechanism for the strong interactions. But yes, it is a short range force. So much of the discussion of QCD actually involves some form of representation theory. So I'll try to keep that off the table and try to give you first a historical perspective on it. And then without proving them, I'll try to flash out the answers and try to convey what it physically means. So in the 30s, actually, let's say Yukawa actually predicted that the force carriers of the strong interactions were some mesons, which are some hadrons, which is called pi meson, and which had a potential like this. So if you remember the potential for electromagnetism, it was some 1 over r in QED, the tree level, of course. However, the description of Yukawa was a non-relativistic one. So a relativistic quantum field theory description actually lacked in Yukawa's theory. So a proposal was that maybe they are described by some SU3 gauge theory. So what Gilman and Zweig did is they classified the hadrons, which are basically baryons and mesons. So basically a bit about hadrons. These are base, as we'll see, these are bound state of quarks. Quarks are the most fundamental particle that we know of, at least that are experimentally known. So what they proposed was they noticed an approximate symmetry, which they call the SU3 flavor symmetry, and tried to build up the theory of baryons and mesons. But this was partially correct. SU3, they correctly identified it, but uh, it created a problem. For example, when people detected the strange quark, which is one of the quarks we'll see, it had a state which was like this. But as we know, quarks are fermions. So 3 of them cannot be in a state. And this violated Pauli exclusion principle. And the proposed solution was that maybe there's some other SU3 gauge group, let's call it color. This was due to Greenberg, Nambu, and Han. So what they proposed is that, sure, but we have now another quantum number, which is the color quantum number, which corresponds to where I, J, K corresponds to red, green, and blue. This has nothing to do with the colors. It's just I think they ran out of names. So it's just a number, and it can take three, each of these indices can take 3 numbers. So furthermore, the development continued, Gell-Mann and Wess, that this SU3 is actually SU3 color, which was proposed to be an exact gauge symmetry. So still, a point to note is that we are still describing a QFT with gauge group SU3. So if you think about it, when we were studying Young-Mills can be SUN gauge theory or something. For this specific case, N is 3. So that is the case. And various experimental support was gained in favor of the SU3 color idea. One of them was, I'll just write the names. which is an experiment very similar to the one that we really know. It's the one of Rutherford where he was throwing gold foils. So alpha particle at gold foils. And this experiment actually said that hadrons, or build up evidence for that hadrons are composite particles, which basically means it's composed of particles of more fundamental nature. And also some QED experiments, some electromagnetic interaction involving uh, electron and positron, we gain support that NC, which if we could have called this NC, is actually 3, or the gauge theory, the gauge group was an SU3 gauge group. So this needs to be studied, as this seems to imply from experiments and of course from theoretical consistencies like this, and the motivation of describing the QFT, that is a relativistic quantum field theory, it, it gave the motivation that SU3 gauge group needs to be studied, as it really might describe, or it really does describe actually, the strong interactions. So QCD, or quantum chromodynamics, is a gauge theory. Let's say gauge symmetry group SU3 color, where our Lagrangian is of this familiar form, which now my force carriers are the gluons, and my fundamental particles are quarks, which are fermions. And if you know a bit of representation, they are in the fundamental representation of SU3. So this we neglect. This is called the theta term of QCD. It has a story of its own. So if you're interested, just search the theta term of QCD, and it leads to one of the most interesting and still unsolved problems of high energy physics. And IJ here, mu nu are, of course, space-time indices, and IJ are color indices. So I'll write down the gauge field, which is so where GS here actually means the coupling constant of the strong interactions.
Do the second capital G, does it have to be B, the index, upper index? Second capital G in the Lagrangian?
Yeah, sure. It has to be contracted, right? Yeah, I mean, I missed it. Yeah, very good. It has to be upstairs. And with the gauge covariant derivative is of this form. So these objects are gluons. And of course, A is an SU3 index, where the generators of SU3 are now some 3 cross 3 matrices. And these are called the Gell-Mann matrices. And it is basically very similar to the Pauli matrix. It's just 3 by 3. And yeah, so you can check that out. You'll have 8 Gell-Mann matrices because SU3 should have 8 generators, right? So one thing to do, I think if you have already not done it, then it's just expand the Lagrangian. That is, you know what these things are. I've written it. It's a very, very trivial exercise. And explicitly check if there are gluon self-interaction terms. Where they present in QED. So you can ask this question and you can check that out. Just expand the Lagrangian and you will see many interesting things popping up. Interesting interaction terms, actually. So a bit about the interaction potentials. Okay, so QCD story goes like this. So you have a strongly, okay, you have a SU3 gauge theory with quarks. That is, of course, if you know a bit of representation theory, they're in the fundamental representation. And that's about it. And they have some gauge indices, color indices. And basically, that's the difference from this traditional Yang-Mills that you have seen. Okay, for QED, if you remember the interaction potential, so let's pick a scattering. We'll pick, let's say, E minus P plus scattering, which is, if you think about in the Feynman diagram perspective, P plus. So one can actually compute things like the scattering amplitude, which is proportional to E squared over the momenta, which you can call V of P tilde. And in momentum space, sorry.
I'm sorry, are these gluon fields, are these vector fields or they're not spinor fields? They're spinor fields?
No, they're vector fields, like spin one. The force carriers are the
Bosons, case bosons, right,
gauge
right.
bosons, right?
Thanks.
So in position space, it takes the well-known formula, a well-known expression, and we know that this is an attractive potential. This is the familiar Coulomb story. If you want, you can reproduce the Coulomb story. This is basically the Coulomb story that we have learned many, many years ago. But for QCD, things are a bit tricky and far more interesting. Let's pick a quark and anti-quark scattering. So it looks like this. Let's call it QJ, QI, Q bar L, Q bar K, which looks like this, which is basically now comes the interesting part. for those, how to say this? Okay, maybe I'll say it just physically. What happens is that in nature we observe quarks confined inside hadrons. For example, protons or neutrons, the familiar particles that we know of, are basically bound states of quarks. So these are singlets. So I'll not go into the detail of the representation, but these are called color singlets because of some representation theory logic or analysis. And the hadrons we see are actually color singlets. For example, mesons are also color singlets. Baryons, for example, this is a combination of, say, neutrons and protons would be. And interestingly, the potential for singlets is an attractive potential. That is minus 4 over 3 gs squared 4 pi r. So this is an attractive potential. So what it does, it creates a bound state of quarks. This is the singlet story, but there's also an octet story, which is basically a repulsive potential. But again, we only observe singlets in nature, that is the mesons and baryons. And all of these are color singlets. And
I'm sorry, in baryons, you have three fermions in a bound state. Does that not violate Pauli exclusion principle? Thank you.
no, why? Can you think?
Sorry?
Can you think why? Okay, can you think when they would violate Pauli exclusion principle?
Uh,
If they have the same type, right? If Qi,
so
let's say I pick,
if you don't have an antiquark, then they wouldn't buy it. Yeah, if they're all of the same type, right, right. Yeah, got it, got it. Thank you.
okay, good. So this does not, of course, violate the exclusion principle because what the epsilon tensor does is that if you have repeated indices, it makes sure it's zero. So that's what's happening inside baryons. And interestingly,
Thank you.
yes,
No, thank you, thank you. Got it. Thanks.
please mute yourself if you're not asking questions. So what happens is that inside baryons and mesons, they form a bound state, and this gives an attractive potential. This gives rise to an attractive potential, and one can easily check that. If you want more details on this, uh, and if you know a bit of representation theory, you can again ask me later. Fernando Quevedo and Andreas Sachner's standard model lectures and the section on QCD, it actually discusses that. So if you know a bit of representation theory, please look into that, and I would love to talk more. Okay, So as I was saying, these color singlets are bound states of quarks, and they give rise to an attractive potential. And this kind of explains why we do not see somewhat, right? Because they are always in a bound state. But this is not the full story, of course, because, for example, I could have said that you could have asked that electrons and protons can have bound states, or any charged particle. We can form a bound state with that. But that doesn't mean that the other particle does not exist freely. So we'll see that in a minute. But this is a way to explain, this is one of the ideas to explain why quarks live in some confined or bound states. This lives, this takes us to the idea of something called asymptotic freedom. Okay. So what happens is, if you have in quantum field theory, if you when you'll do the course maybe on renormalization, you'll see something that couplings are renormalized. That is, they get a contribution from uh, fields running in loops. Specifically, if you have seen, let's say, this diagram, let's say in a gauge boson connecting two particles, that is an interaction diagram. So this has another QFT contribution, which we have not studied here, is if we can have loops of matter and gauge fields. For QED, we did not have loops corresponding to some photon self-interaction, but for Young-Mills series, and specifically for QCD, this is an effect that you'll have now gauge fields with different kinds of interaction running in loops. And this gives an interesting effect that the coupling behaves in a very interesting way. So what happens is that let's define a quantity, which we call B. So this is the flavors. We'll see that in a minute. And this is our familiar color, right? It is 3 because we are dealing with the SU3 color. So what happens is that there are two interesting phases. Let's say this is my cutoff of the theory, and this is some energy scale. This is, let's say, for B greater than 0. This is my cutoff of the theory, and this is for B less than 0. Yeah. So this is a very special feature that only Young-Mills theories display. And I think Gross and Wilczek found this out. And this has a very interesting property because what it says is that as you increase your energy, this GS or G strong is the coupling of, or the strength of coupling of quarks or anything in the QCD channel. So what it says is that as you go into higher and higher energies, quarks become asymptotically free in the sense that as you take two quarks closer and closer together, it behaves as if they're free particles because the strength of interaction decreases. So this is a very interesting behavior because this is unlike what we see in electromagnetism, where if we bring two particles closer together, the strength of the potential actually increases. But something opposite is happening. As you bring them closer and closer together, or as you increase the energies, whichever language you like to speak, these become asymptotically free. As if quarks behave as if they're free particles. So for QCD, this is 3 and this is 6. And B is 4 minus 11, it's a positive number. Sorry, 11 minus 4, so it's a positive number. And QCD actually is realizing this aspect of Yang-Mills theories. So what is happening is couplings getting smaller and smaller with energy, and why we use the word asymptotically, because as energy increases and grows to zero, there's a time when this, or at infinite energy, it behaves as a free particle. That's what we mean. So, but however, we heard the stories that QCD is at strong coupling. This is because we are looking at energies below the QCD cutoff. So at low energies, it is a strongly coupled theory. But at high energies, it is actually as if they're free particles, or it is a weakly coupled QFT. So this is a very interesting behavior of QCD, and also it appears in many Yang-Mills systems. And this is what makes QCD more unique than electroweak interactions. And this is how the interaction strengths are actually short-ranged, because the bound states that we observe, quarks are confined together. That is why the uh, quarks are bound together. That is why the the force is short-ranged. So this is the story of QCD.
The diagram on the right, that's the QED diagram. With higher energy, the coupling is getting higher and higher. So that's the QED picture, right?
This expression is actually for Yang-Mills, but a similar thing happens in QED.
Okay, got it. Thanks.
So what did we learn about QCD? One is this is a gauge theory, SU3. And second, So this is an attractive potential. N3, free at high energies. And below QCD scale, confined inside hadrons. So this is the story of strong interactions that I wanted to quickly convey. So let's put standard model all at once. So the full standard model is a theory with gauge group SU3 color, SU2 left, U1 hypercharge, which is spontaneously broken. We saw this Glashow-Salam-Weinberg theory and how the spontaneous symmetry breaking works in action, which is broken to this combination. So before SSB, the gauge fields were these, and after SSB, we have so from which these are massive, but the gluon is massless, but confinement actually restricts it to be inside, and it is a short range force. So the gauge part is plus the theta terms. There are some terms which are topological and they do not appear in the equation of motion, but they have very, very, very interesting uh, implications for the physics. Okay, so we had the fermionic matter content I did not really specify, or I did not really talk about in depth, but we have the quarks, and let's do this. We have 6 flavors: up, down, charm, strange, top, bottom. And we had, of course, the right-handed ones are there, except for the neutrino, which because of the weak interactions, we saw that there's no right-handed neutrino. Similarly, we have the leptonic parts, which are the left-handed ones. These are electron, muon, and tauon, and their corresponding neutrinos. And of course, we have the right-handed counterparts. We also had the right-handed here, of course. And there's a star here. There could be some right-handed counterparts, which I'll say a few things at the end. So about standard model, as we see it, there are more than 25 free parameters. And what are those parameters? Starting from the uh, value of the Higgs, the value of the minima of the Higgs, to masses of all of these guys, then Yukawa couplings, that is the couplings between fermions and bosons. And you have the 4 of these three of these coupling strengths, which are the weak interaction strength. Then you have the coupling strength corresponding to the photons and all. So there are 25, more than 25 free parameters, and more if there's a right-handed neutrino, and more on this later, but there are more than 25 free parameters, which of course takes the value as we get from experiments. A comment about standard model, as we should know, it is renormalizable, which basically means it is free of infinities and ugly business, and anomaly free. So, and this anomaly is basically saying that anomaly is basically classical symmetry which do not survive as we go to some quantum process, which do not survive quantumness, let's say. And the standard model Lagrangian is, of course, you know that somehow we live in 4 dimensions, and this is in mass dimension. Lagrangian has mass dimension 4, this guy -4, because Lagrangian needs to have mass dimension 4 because the action is dimensionless. And standard model, all of the standard model parameters, or sorry, all of the standard model terms in the Lagrangian, standard model Lagrangian, of course, has to obey this. So one can see that each of these do appear in the standard model. Also, a bit of note is that, let's do this. Maybe. Sorry. So a bit of note is that, for example, theta equal to 0, where theta are the terms in the, for example, uh, for example, this could be a theta. The key. These guys are thetas, and these guys are strength of couplings. For example, m square phi squared, or lambda cube, sorry, lambda phi cubed, or g phi to the fourth, and so on. So these are m squared, lambda, and g, and these are basically the terms that are appearing in our Lagrangian. So for a term of mass dimension 0, there is actually a term, which is what we have seen very recently, is that the constant term in the scalar potential. One second. That is, it is proportional to lambda v to the fourth square. There was a constant term. If you really do the expansion of the GSW, you'll see this term. It's coming from the Higgs, of course, it's visible. There are terms which are like this. Which is basically C2 is m squared, and this is the m square 8 squared term. That is the mass of the Higgs term is mass dimension 2. And the coupling has also mass dimension 2. 3, there's nothing of this sort in the standard model. And 4, so what we are doing is we are grouping all the terms in the standard model Lagrangian. So this has the most terms, like all other terms, like gauge couplings, Yukawa, and so on. So this is how we identify all the terms in the standard. We can group all the terms in the standard model. One way to do that is via their mass dimension, or the mass dimension of the operators or terms appearing in the Lagrangian. So maybe it's a good stopping point. We'll take a quick break and come back in 5 minutes. Maybe it's best to stop the recording for now.
Okay, maybe we can keep the recording on because then we will have one coherent file if that's okay with you.
Yeah, sure, sure. So if you have any questions, it's a good time to ask before we start.
I asked you a couple of questions on the chat there.
Yeah, it's in GeV. Physically, why do we not see the, I mean, it does not appear. I mean, there's there's no such term that is, there's no cubic mass dimension term in the standard model Lagrangian. There's no
Is
requirement
that
that there
because
should be. There's no requirement that there should be a cubic term with a certain mass dimension, but it does not, there's no such term.
is it because of experimental observations or just
No, it's just there's no term such that. There's no experimental input on what terms should be there in the Lagrangian, but a consistent story of the universe, at least fundamental particles, can still be told without having a cubic term.
okay? Thanks.
You don't know. When you expand, there are some terms that lead to non-renormalizable theory. Cubic term in 4 dimensions, not exactly, but it has some issues when you have, for example, if you think about a phi cube term, it's a good point. So it runs down like this. Think of an x cube graph, which is this, something like this. So there's no potential stable minima where you can study physics. That is a problem with cubic terms. But yeah, good point.
I'm sorry, maybe I'm jumping ahead. Can you talk about QCD on the lattice, like Wilson loops, Haar measure, and plackets and stuff like that?
You can, people study those lattice QCD stuff.
Yeah.
Yeah, people do study that.
You're not going to discuss that
No,
here, right?
no.
Okay. All right. Thanks.
Okay, maybe we can start because I'll just say a few more things. So we have seen the standard model in action, that we have some GSW model which spontaneously breaks to U1 of electromagnetism. And in return, it gives us that the three of the chart of the gauge bosons are massive. And it's a very interesting story that we studied. For QCD, the story is a bit different, and it's still very interesting, is that uh, due to confinement, we have a short-ranged force, as we saw that the potential is attractive. And most interestingly, the QCD coupling actually shows one of a very unique behavior that we have not seen before, that at high enough energies, it behaves as if the coupling is going to zero. So the strength of the force actually decreases. That is, quarks are asymptotically free at high energies. So I'll quickly summarize. Maybe this is still an understatement. The success of the standard model.
I'm sorry. It makes physical sense, or it makes, I don't know, intuitive sense that higher energies would lead to more freeness, if you will. It is kind of odd that at higher energies you have more. In the QED picture, you have higher couplings. Would you agree?
I don't think so, because okay, I can make sense of both of them, but if you think about it, all of the particles that you see in nature, for example, if you bring two magnets very close, the force decreases, right? Increases, sorry. So that's the
Right.
case with every other fundamental interactions that we saw. But QCD, what it says is as you bring them close enough, if you're bringing them closer and closer and closer and closer, it's behaving as if there's literally no force between them.
What I'm trying to picture trying to picture now is the oscillation of the field. So you have more and more high energy, the field is going to oscillate more. And of course, the particles are excitations of the field. So it makes intuitive sense that if you give in more and more energy, the particle is going to oscillate more and is going to be more free of other interactions. So there is going to be less interactions with other excitations in the field. That makes sense. But in the QED picture, I'll think about
Okay,
that.
okay, maybe
That's
think
that's
about
a
that.
general comment. Yeah.
Think about that. Maybe after the lecture we can ask. So, what is the success of the standard model? So, every particle physics experiment done to date, for example, the QED experiments, electroweak, strong interaction, QCD, all, and to a extremely high precision, very high precision, in a sense that we have not even seen, for example, for the known interactions, we have not even seen any deviation from the results predicted by the standard model. And of course, it explains, for example, uh, it makes predictions or made predictions. For example, Higgs, which was later confirmed by experiments, like in 2012 or 13, I think, we discovered the Higgs boson at CERN. And it just not it does it just does not only explains, let's say, what the experiments before, the experimental results before, it also explains anything that we have done until now, and to an arbitrarily high precision. So there's precision tests going around all over the world in detectors like CERN and the Fermilab, and still we have not found any deviation from what we expect from the standard model, so which is pretty amazing. And of course, as we saw, is mathematically consistent. Consistent in a sense that it has no anomalies and is renormalizable. So is it the end of the story then? So if, for example, if it explains every experiment is mathematically consistent, so should we stop doing physics? So in the last part, or in the last 20 minutes, let me highlight some problems of the standard model. Plus, on top of that, how can we go beyond, or how to go beyond SM? The first part is why to go beyond SM, and the second part is how. So first off, my favorite avenue is cosmology problems. So there are certain problems of the standard model that, for example, if you know about something called dark energy, so it's basically it's around 70% of all matter and energy in the universe, and it's actually driving the expansion of the universe. In some ways, it can be explained in one of the way to explain it, if you know about Einstein equations, is via a cosmological constant term. Of course, you can do more. You can have some certain fields, this scalar fields describing that. But anything from the standard model does not really fit into the criteria of explaining dark energy. And more interestingly, one can try to do a calculation where the QFT prediction or the standard model, let's call it standard model prediction, and our current observation of dark energy is off by 10 to the 120 orders of magnitude. That's a huge number, like 120 zeros after 10. So that is a huge mismatch between theory and experiment. So it really fails when we apply standard model, of course, the naive vanilla standard model to explaining the dark energy. That is something that is around 70% of all matter and energy content in the universe, and it's also probably driving the expansion of the universe. So that is a big issue of the standard model. And of course, something called dark matter. Again, it's an invisible form of matter. So when it's around 25%, I think, of the matter in the universe, and it is not explained by standard model. So if you think about the energy budget of the universe, it's around 70% dark energy, 25% dark matter, and 5% ordinary matter, which is okay, somewhat explained by standard model. So this is another avenue of issues. Another one is something called an inflation. There's also a star about inflation. So observations suggest that the early universe went through a rapid expansion of space and time, probably by some scalar field. And this is not explained in the standard model. So there's no scalar field, or let's say if the inflation was done by some scalar field, that is an very, very rapid expansion of space and time in the early universe, which explains our observational bounds as well. And interestingly, there are no standard model fields that can do that job. This Higgs was a good candidate, but I think current observation suggests that it cannot be the Higgs. But so some form of particle, let's say, if we think about a QFT picture, it cannot describe the very early universe. And of course, not even the late or current time. Let's call it. Second problem is gravity, which is of course related to the first problem of. But standard model explains all of the three fundamental forces except gravity. So when one tries to, let's say, quantize gravity the traditional way, it runs into again renormalizability issues and some basically nonsensical answers involving infinities. But we know, or we expect, quantum effects of gravity to kick in at a scale called M Planck, where gravity becomes, if there's a coupling of gravity, gravity becomes what we say is strongly coupled. So there's a description. So the standard model really fails to capture one of the major fundamental forces. And of course, there's even aside from this, you can ask more philosophical questions like why GSU2, SU3 cross SU2, U1. There's no answer about that. But maybe this is more of a philosophical question, but you could have also asked a more scientific question, is that why, let's say, 20 plus parameters or 25 plus parameters? And this is worrying because these are free parameters and we have no explanation why they are the way they are. Maybe there should be some explanation because 20 plus parameters is a lot of parameters. And then there is another major problem called the hierarchy problem. So in QFT, as we said, For example, if you think about a Coulomb potential, which is basically exchange of photon between two particles, but there is a prediction from QFT, which of course matches to a very high degree precision, that when a photon is going through, it can form a loops, it can run, it can decompose, if you think about it, into two particles of opposite charge, of course, since the photon is chargeless. And for example, electron and positron or something. And this run in the loops, and this contribute to the computation of my potential between two particles. So this is a, let's say, a QED thing. This is a classical thing. But of course, if we have given this a quantum field theory picture, but this is a QED thing. And this is what happens when we measure, for example, the Coulomb potential and the QED coupling, which agrees with experiments to an unbelievable. So what it backfires is that it also gives a correction to the mass of the Higgs. So every parameter in the standard model gets quantum corrections. So for example, if you can think of a coupling, that will also get a quantum correction. That is, it will be something called renormalized, or so these couplings get a correction proportional to, let's say, some this Higgs mass getting correction. When what I mean by delta M Higgs is a correction to the Higgs mass. I think there's a square here. I'm not sure, but some powers of. So which is the cutoff of our theory? And if someone comes around and claims that, let's say, the standard model is valid up to, let's say, the Planck scale, then the correction to the Higgs mass is more than Higgs mass itself. So the Higgs mass is not stable. And this is a problem because how can the correction to something be bigger than the quantity itself? And this problem is actually called, for example, if this is M Planck, the correction would be absolutely huge. This is called the hierarchy problem, or a more general version of it. This is called a technical hierarchy problem, but a more easier version of it is why the, let's say, electroweak scale is much, much less than the scale of gravity, or M Planck. Let's call it gravity, let's say. Or why gravity is the weakest force. So this is a technical version of the same problem, the hierarchy problem. Then there are problems like the strong CP problem. So this relates to a term that I did not write down in the Lagrangian. It's called the theta term. For example, QCD has a term like this. Where G mu nu tilde is basically epsilon mu nu. So what experiments suggest that this theta is an extremely small number. If I remember correctly, it's smaller than 10 to the minus 10 or something. This is from consistency and experiments. Their term should be there for consistency, and experiments suggest that since it is there, it is extremely small. This relates to a story of anomalies, which you can just look around into the notes by Fernando. And we don't have an explanation from the standard model why this is such a small number. Then another problem is the problem of neutrino mass. So observations actually suggest, that is, neutrino oscillation experiments actually suggest that neutrinos might have a mass. So if they have a mass, if you remember how we wrote down mass terms for fermions, right? you had the left-handed guy and the right-handed guy to write down a mass term for the fermions. And if there's such a mass term for the neutrinos, then it suggests there should be a right-handed neutrino. There's no mechanism in standard model actually explaining why neutrinos should be massive or right-handed neutrinos should be there. Okay, so what is the way out? Or what can we do to address these problems more systematically or
Now,
more?
I'm sorry to interrupt, but on the neutrino problem, I think we have a I think we have an upper limit on their mass, but we don't know whether there is a whether they're massless, right? Do you have any comments on that?
Yeah, actually, so neutrino oscillation experiments reveal that neutrinos, uh, easier way to say this, have a very tiny mass actually, very tiny mass. They're not massless. So if they have a tiny mass, of course you can, I don't know if you, yeah. So one of the ways to explain it is by something called a seesaw mechanism. It's a way to generate a mass, but it is not within the framework of standard model. And my comment is that, yeah, and that neutrinos have a very small mass. That's what observations suggest.
Okay, thank you.
So the ways out is one is supersymmetry. So a good resource for this, in this part, I'll keep out pointing. So Fernando Quevedo's notes on lecture notes on uh, supersymmetry and extra dimension. I think it's a good time for you to maybe look into those. These are very fun lectures. There's videos of it as well. So supersymmetry basically starts off with a very basic question. So if you remember to our very, very, very early days of this course, Orpith was discussing generators of quantum field theory. And interestingly, all of those generators are bosonic generators. There's no fermionic generators in the quantum field theory course we studied. So, so one can do something is that one can minimally extend the standard model by including fermionic generators. And there are theorems by Haag and Lupazansky, which shows that actually it is consistent if you include, you can have a consistent QFT and quantum field theory really allows you for, let's say, Lorentz invariance, unitarity, S matrix, positivity, blah, 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 uh, allows for such generators to exist. And once you include that, a very interesting thing happens is that every bosonic field that we saw, every particle has a supersymmetric partner. What does it mean? For example, every boson has a fermionic superpartner. For example, the Higgs's superpartner would be some particle which is a spin 1/2, which is related by this symmetry, which we call supersymmetry. And they have spin 1/2, and they're sometimes called Higgsino or something. Though the electron would have a superpartner called the selectron, which is again a scalar. So every particle has a every bosonic particle has a fermionic superpartner, every fermionic particle has a bosonic superpartner. So if then the gauge bosons, there are gauginos and blah, blah, blah. And what it does is that this small extension of including fermionic generators to the standard model actually saves us in many ways. One, how does it save us? Let's call it A. It addresses the hierarchy problem. That is, the correction to Higgs can be such that it is cancelled due to some symmetry. So naively speaking, if you have bosons running in the loop, you have fermions with the same mass and charge running in the loop, and they come with opposite signs, and they cancel very nicely. So it addresses the hierarchy problem. It also addresses in some part, coupling unification. For example, one thing we saw is that at high energies, electroweak interactions, which is basically weak interactions and electromagnetism, are part of the same force. But a coupling unification happens under this arena. Also, it has particles which can explain the dark matter abundance. So that is nice. And in some ways, it can explain inflation. So it addresses quite a few things, but the gravity version of it, at least in 4 dimension, which we call supergravity. So in 4D is again not renormalizable. So it could be it is not part of the full story. That is, it cannot fix the problem of gravity, but in some ways it can address some of the few problems that we saw of the standard model. Second, which are called grand unified theories. So anomaly cancellation and blah, 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 those story actually allows for two gauge groups which are close together, which is basically embedding the standard model in a bigger gauge group. So one thing it helps us is again coupling unification. That is, at high energies, all of the couplings merge towards or tends to merge towards a single coupling. So all of these part of a bigger or under the umbrella of the same force. And in some ways, it can address neutrino mass. And there are some cases where it can address inflation. So I should write the prediction of this. So the prediction, if we live in a universe which really addresses supersymmetry, the prediction of it would be observing supersymmetric partners. And the prediction of this guy would be maybe proton decay. So gut theories actually imply that protons should decay, basically baryon number violation, which is a standard model symmetry, but it's not a symmetry for the guts. And lastly is the most ambitious of them all is quantum gravity. So maybe the problems we face of the standard model are not due to expanding just in some way the standard model. Maybe it involves a paradigm shift of what we have been thinking. So one of the major candidates for quantum gravity is something called string theory. So this is the only UV complete, that is, it has no infinity issues, renormalizability issues, and produces gravity consistently, and also produces Yang-Mills theories. So in a sense that it is the only available version or only quantum gravity that we know of that is consistent and basically unites quantum mechanics and uh, gravity together. So one can have, let's say, for example, if we go to the basics, we had quantum mechanics, which again is replaced by QFT. And we have a QFT framework. For example, again, at low energies, this is Newtonian mechanics. But if you think about it, Newtonian mechanics also gives rise to SR and GR. And this should be a binding point of what quantum gravity should be doing or should be explaining. That at low energies, it should reduce to standard model. And at some certain limits, it should also reduce to general relativity and of course, special version of it as well. And in certain limits, this of course happens because this is a consistency that we checked throughout the history of physics. So when we had quantum field theory, at low energies, we should be able to deal with quantum mechanics. We should be able, at much lower energies, we should be able to deal with Newtonian mechanics. And that's what we deal with every day in our lives. That we rarely use quantum field theory in everyday life. But yeah, of course, quantum mechanics and Newtonian mechanics and special relativity do feature in our lives still. So very quickly, I'll say what happens in the case of string theory or a quantum gravity theory is supposed to do is the story of string theory is very simple. You have a relativistic string, you quantize it, and you have dynamically given rise to gravity, that is the metric, plus Yang-Mills theories plus scalars. So this arises dynamically when we quantize a relativistic string. And more interestingly, it just has one parameter, that is the string length. Let's call it LS. So everything, for context, standard model has, of course, more than 20 parameters. String theory just has one parameter. And more interestingly, in standard model, as I was saying, or as we fixed before, we gave dimension was an input of our theory. There were many inputs, and dimension of spacetime was an input. That is, we fixed the dimension to be 4. But what happens in string theory is that dimension is forced by or fixed by consistency of the theory. So that is very interesting observation that we had of quantum gravity, that of a quantum gravity theory, that it was forcing us to fix the dimension of our spacetime, which we never had the privilege when we were doing standard model. Of course, it addresses problem like cosmology problems is very nicely addressed under the banner of string theory. For example, dark energy, dark matter, inflation.
What do you mean by consistency? Sorry.
Yeah, I'll come back to that. So of course, particle physics problems like, for example, the ones we saw, every problem that we saw above has an embedding or has a string theory has a story to tell about these. For example, parameters that we saw, like the 20 plus parameters, arise dynamically, in a sense that, for example, we fix the parameters, but string theory actually tells us how the parameters should be of the standard model, or in an ideal world. And this is a bit more on the formal side, like strongly coupled QFTs can be addressed. So we have something called the holographic duality, which lets us tell a story of strongly coupled QFT by looking at some other picture. Also, it gives, I'll not say that the last point, but it also gives a nice description of the absence of anomaly conditions in terms of geometry. And of course, it has a richer story to tell, as any quantum gravity should be telling us about standard model or physics at lower energies compared to the scale of quantum gravity. Okay. Maybe I'll stop and then take questions for the rest of my time. Can you stop the recording?